Buoyancy and Archimedes' principle. Earlier, we saw this image while we were defining pressure. You might have noticed that the arrows pushing down on the top of the submerged object were shorter than the arrows pressing up on the bottom. Since the pressure due to a fluid increases with depth, there is greater pressure at the bottom of the object than at the top. If an object is submerged in a fluid, there is a net force directed upwards on the object because the pressure is greater at the bottom of the object than at the top of the object. This is called the buoyant force, or F sub B. So here we have a little derivation. You can see that the buoyant force is going to be the difference between this force and that force. So there's a force due to the pressure at this depth in the liquid, right? We have all these little molecules bouncing around, and the net force is going to be perpendicular this way. We have a bunch of molecules up here all moving around, pushing in all directions, but also pushing straight down on this object. The difference in those forces is going to give us a net force upwards, the buoyant force. Now, force is pressure times area, because pressure by definition is force over area. Therefore, force is area times pressure. And we've already figured out that the pressure due to a fluid is rho GH. So instead of this P sub 2, we can have the density of the fluid times G times the depth at that point times area, right? So the cross-sectional area that is of the submerged object also plays a role here. So we have the buoyant force. We can factor out rho GA, and we have that height difference, which is basically just the height of the object itself, right? Because you're gonna have one pressure at this height, a different pressure at the bottom. That height difference is here. Now, A times that height difference, well, A is the area of this side of the cube, right? And the height difference is here. If we multiply those together, that is volume. That is the volume of the object. So what else do we have here? Oh, well, remember, density by definition is mass per unit volume. Therefore, if we have density times volume, that is equal to mass, right? Mass equals rho V. So we have rho times V, so we can replace that with M. So the net force due to fluid pressure is proportional to the height of the block, and it's actually equal to the weight of the displaced fluid. So we'll get into that on the next slide. The upward buoyant force on an object immersed in a fluid, partially or completely, is equal to the weight of the displaced fluid. So if we have this object here that is submerged, the buoyant force, the force upwards on this object, is equal to the weight of the water that would have been there had the object not been there. All right, here we have a picture of a polar bear holding a ball underwater. So if you've ever been to the beach, you know that taking a beach ball and trying to submerge it completely in a pool is difficult, and that's because of the buoyant force. So let's draw a free body diagram. We're going to assume that the beach ball is stationary currently in this picture. So the buoyant force is the force upwards, and that's due to the fluid, the pressure due to the fluid being different at different heights, submerged underwater, right? Another force is the bear pushing down. And the third force acting here is the earth pulling down on the plastic ball and the air inside it. And you can see that since this ball is stationary, there is no acceleration, which means the force up must be equal to the forces down when you add those together. Now let's look at the same picture with Archimedes' principle. The buoyant force on the ball is equal to the weight of the displaced fluid. To find the weight of the displaced water due to this ball being underwater, we need to find the volume of the water that is displaced by this ball. The volume of water displaced by the ball is equal to the volume of the ball, since the entire ball is underwater. Since mass is equal to density times volume, right? Density is mass over volume, therefore mass equals density times volume. The weight of the water will be equal to, so remember force, the weight is the force of gravity, right? So we have m times g. This is going to be the weight of the displaced water, and that's going to be equal to the density of the water, the volume of the water. So we have m, rho, and v, and we've just multiplied both sides by g to get so that this would become weight instead of just mass of water. And we end up with rho vg on the right side. So the buoyant force is equal to the weight of the displaced fluid. So this is the mass of the fluid times g, which is, the force of gravity. The buoyant force is also equal to the density of the fluid times the volume of the fluid times g. So these are equivalent. The net force on an immersed object is the difference between the buoyant force and the gravitational force. So here, if we hang a cube made of a material from a spring and it's stationary, we know that the force exerted by the spring on the object must be opposite and equal to the force due to the gravitational pull of Earth, right? So F scale equals mg, the weight of the object. If we now take that setup and submerge it in a fluid, we've also added in this buoyant force. But because this object is still stationary, it's not accelerating, that means that the force of the scale plus the buoyant force must now be equal to the weight of the object. Remember, for a motionless object, the net force on it is 0. And that's also true for objects moving at constant velocity. But in this case, this object is stationary. If you've ever tried to push a beach ball downwards into water, you felt the buoyant force resisting your attempt. The buoyant force is not dependent on the object's depth in the fluid, since only the difference in height of the top and bottom matter. As an object sinks in a fluid, that difference in height between the top and bottom of the object remains constant. Both orange squares have the same buoyant force acting on them. If these are two cubes, right, in the water, this one is lower in the water, but the buoyant force is the same as this one. You could also think of it as these two identical cubes are both displacing the same amount of water, which means they have the same buoyant force acting on them, since the buoyant force is equal to the weight of the displaced liquid. All right, any floating object displaces its own weight of fluid. So if we draw a free body diagram for this boat floating in water, we have the earth pulling down on the boat, right? The weight of the boat, the mass of the boat times g, and the buoyant force is pushing up. Those must be opposite and equal. Consider an object of volume v0 and density ρ0 placed in a fluid of density ρf, F for fluid. If the density of the object is less than the density of the fluid, there will be a net upward force until the buoyant force balances the object's weight, and only part of the object's volume remains submerged. So this is what happens when something floats, right? So we have a free body diagram here. There's the weight of the object, and there's the buoyant force. Now remember, the buoyant force is going to be the weight of the displaced fluid. And so the weight of the fluid is mg. But remember, because density is mass over volume, you can replace m with rho v. So that's how we get this equation here. For rho, the density of the fluid, times g times the volume of displaced fluid. So this volume here, not the full volume, just the submerged portion. That's going to be your buoyant force up. That must be equal to the entire weight of the whole object down, right? Because the earth is pulling down on the whole object. The fraction of the volume submerged is given by this ratio of the object's density to the fluid's density. So here we have the buoyant force is equal to the weight of the displaced fluid. We have this equation here for the weight of the displaced fluid. We have this equation here for the density of the object times the volume of the object. This is just mg, the weight of the entire object, right? We could express mass in terms of density times volume of the whole object, not just the submerged portion. Then we see the g's cancel, and we have this ratio here. So we can say that the volume that is displaced here is to the entire volume as the density of the whole object is to the density of the fluid. The ratio of the density of a substance to that of a standard substance is known as specific gravity. The standard substance almost always used for liquids is water at its densest at 4 degrees Celsius with a density of 1,000 kilograms per cubic meter. So specific gravity equals the density of a substance divided by the density of water. A substance with a specific gravity less than 1 means that it is less dense than water. So this number ends up being smaller than the denominator. So this entire fraction ends up being less than 1, right? It could be 0.7, 0.8. That means that the substance is less dense than water. It will float on water. And a substance with a specific gravity greater than 1 means that the numerator must be greater than the denominator, which means that the substance is more dense than water and will sink. You can compare the densities of different objects by seeing how much of the object is submerged while floating. So this is like 2 slides ago when we were saying that the volume that's submerged divided by the total volume of the object is going to be equal to the density of the object divided by the density of the fluid. This is specific gravity, right? So this is going to be water in this case. This is going to be the density of the object. And this is going to give us what percentage of that object will be underwater. So block A is 25% submerged in water as it floats. You could say 0.25, right? Therefore, its density is 25% that of water. Block D is fully submerged but stationary. That means that block D has exactly the same density as water. You could also use this method to compare the densities of various objects to liquids other than water.